Good morning, everyone. Can you guys hear me at the back? Can you guys hear me? Okay. So while people are slowly walking in, are there any questions? Anything from the last lectures that you would need an explanation for, or if there's any confusion, any questions? Okay. So today we would start looking into neural networks. Basically, we have developed all the tools that we need to design the cost function for a neural network and finding the optimum weights of the neural network for any regression problem that we have. Today we would see what to do in the case of a classification problem and how to set it up, and then we would try to solve it with a simple neural network. And then the idea is extendable to deep networks as well. Okay. I'll just wait a minute for everyone to come in and then we'll start. Okay. So this is the outline for today. You would start by looking into classification. So if you remember, for supervised machine learning, we had two classes of problems. One was regression and one was classification. So in regression, the relation between your data, the input and the output, is a continuous function. So, and you're trying to learn it. In classification, it's just a few discrete values. So you have to tell which class your data point belong to. A simple example would be, let's say you're looking at images and you're trying to say, let's say if there are cats in it or dogs in it. So it's a discrete output. Either 1 for a cat or 0 for a dog in this case. Okay. So of course this problem, if you have discrete outputs, it's not a continuous problem, and all the framework we have developed for solving our problem is based on gradients, right? And for discrete output, gradients are not well defined, right? So we would have to do some work around to solve this problem, right? And for that we would need activation functions, and then for different activation functions we might have different cost functions. We'll see what each of these terms mean and how we use it. And then we would see how to use neural networks for a classification problem. Okay. So here is a quick recap of what we have done so far. We have learned to solve problems like this, right? You have some data and you want to fit a function to it through regression, linear regression. Okay. So I have a question for you guys. I have 3 results for linear regression. One is a simple line, so I can guess that I have just one polynomial base and a bias term in it. So it's just the function that I'm trying to model is theta 0 plus theta 1 times x, and I'm learning the weight of theta 0 and theta 1. Okay. Then I have a function which probably has slightly more polynomial bases, maybe x power 4 or something like that. And then I have one in which you have probably quite a lot of polynomial bases, maybe x power 10 up till x power 10. So which one of these would you select as the best answer for your problem? If you're given these three results, and you're asked, okay, which is the best model for the data, which is the best hypothesis function that you can learn for this data, which one would you choose? Yes, the second one. Okay, so one of the suggestions is to use the second one. So then, of course, I would ask a question, why not the third one? It goes through all the data, right? So it's the answer is that it's an overfit, and we would see in the next slide what does an overfit mean. Okay, so that was regression. How would a classification problem look? So a classification problem looks like this. You have two-dimensional input data, x1 and x2, and you want to classify it into two classes, either belonging to the class of circles or crosses. Okay, so let's say in this example I denote circles by class 1 and crosses by class 0. So I have to tell, if I'm given a point in xy plane, I have to tell whether it belongs to class 1 or class 0. Okay, so basically I have to make a decision based on a given input how to give it a class label. Again, I'll ask the same question. If you're given these three, which one do you think is the best answer? And I think most of you would say the middle one, because this seems like an underfit and this seems like an overfit. But let's see, how do we formulate this problem of assigning a label? So let's say that this is my problem, and given an xy, I want to give a class label to it. So I can actually formulate this problem in a way where I say that if a point is above this blue line, give it a label +1, and if it's below this line, give it a label 0. How we would do it, that's something that would come, but that's what I'm proposing. That on one side of this line, which is my decision boundary, I'm basing my decision on this line. I assign one class label, and on the other side I assign another class label. And we would see in the coming slide how to do it. Okay, so let's first look into what exactly is an underfit and an overfit. Okay, so we saw this example. Let's say I am giving, so I will draw some data points. Okay, and let's say at the training time, when I was training my data, I took a subset of this data. Let's say this and this and maybe this. Okay, now as I increase the complexity of my hypothesis function, maybe for the lowest complexity I would learn something like this. So I have, let's say, two bases, the bias and the first power of x. I increase the number of bases in my hypothesis function slightly, and maybe I'll get something like this. So let's say it says 4 bases, and I increase it even more, and maybe I get something like this. Okay, so let's say this has, let's say, 10 bases. Now if you look at it, if you look at the black curve, it fits the data, the training data perfectly, but it's a very bad approximation of my function, right? Because I have the other red points as well, which are not available at the training time, but which are a true representation of my function. So I don't want a hypothesis function which fits my training data perfectly, but does not fit any other data that I have not seen at that time. Okay, I want something in the middle which fits the training data well, but if there is a sample or a data point which is not in training data, it fits that as well. So a question that you guys should ask is that that's a very difficult problem. I cannot model all the test data that I haven't seen yet. How do I do? So I have training data. I don't know what test data would I get. So how do I eliminate this problem when I just have training data while I'm training my network? So the solution is actually quite simple. Yes? No, if we can, we will try like to get 100% accuracy. For example, if you have something like this, where we are certain that all the data is like this, of course we want to get 100% accuracy. But again, we don't have a limit on accuracy. We have the limit on the collective accuracy on both the test set and the train set. So we don't want to get high accuracy on train set and low accuracy on test set. We want to get something which is good on both. Yeah, which is reasonable on both. And how do we do it? So let's say you are given, let's say this is your training data set. Okay, you have to train your neural network or any machine learning algorithm on this. So what you say is typically, maybe you say that 80% of this data I would use for training and 20% of this data I would use for testing. And that's called a validation data set or validation set. So when you're training, you don't show this data to your algorithm. Okay? And you see how the network is doing on that. So now let's see if I have my model complexity on x-axis and I have my, let's say, error on y-axis, and I start, let's say, looking at this example. When I have low complexity, my error is large. As I increase my complexity, my error is decreasing. It's decreasing. Depending on the case it might even reach zero. In some cases it might not, depending on how your data is. But the complexity would decrease, the error would decrease as you increase model complexity. But at the same time, if you are plotting the error for validation set, you would see that in the when you have low complexity, the error for the validation set is high, like it is for the training set. It decreases until a certain point, and after that, while the training error is decreasing, the validation error would start increasing. Okay, so basically this is the point where you would like to stop. Okay, so this is like the perfect complexity for your problem. So you don't want to, let me just write this. So this is the training error or training set error, and this is the validation set error. So as soon as the validation error starts increasing, of course the training error is still decreasing, but we don't care anymore. It means that we are just overfitting to the data that we have. We are not learning what the model is telling us. So we stop. We would say that, okay, this is the complexity that is enough for us. We don't want anything more. Okay? Does it make sense to everyone? Yes. Yeah, sure, absolutely. So you understand what I mean by model complexity, right? It's the number, in the case of linear regression, it's the number of polynomial bases I'm taking in my hypothesis function. So if I'm taking just, let's say, a bias term and an x, like the first power of x, my hypothesis function is theta 0 plus theta 1 times x. So the hypothesis function would be a line, it would be a linear function, right? Okay? And if you're trying to see the error between your hypothesis function and the observed data, it would be high, because our function is slightly complex. It's somewhat like maybe x to the power 4 or something like that. It needs some higher polynomial bases. So the error is high. As you increase the number of polynomial bases, let's say from x power 1 you went to x power 2, so now your hypothesis function is theta 0 plus theta 1 x plus theta 2 x square. So you see that your model, your hypothesis function would probably fit your data slightly better, so your error would decrease, training error would decrease. Okay, and as you go along you would come to a point which is represented by this black line. Okay, now if you look at this black line, your training error is almost zero, because it's going through all the training, it's going through all the points of the training set. The training set is highlighted by the green circles around the data points. So the training error is very low, you're somewhere here. But if you look at the error for the validation sets are all these other red points. So the error is huge. So it means that past a certain point, your validation error starts increasing because you are just overfitting to the data. Okay? Because the data has some true property of the function that you're trying to learn, and then it has some error, some noise, and then you're trying to cache the noise. So it's an overfitting problem. You're going into the domain of overfitting, something which is not representative of your underlying process, but rather maybe is a result of a noise in your measuring technique or something like that. And you don't want that. You want to stop at that point. You say, no, let's not overfit. Let's take a complexity which works, model complexity which works well for both the training set and the validation set. So that's basically the point where you would stop, and this is the model that you would choose for your problem. Is it clear? Any questions? Okay. So with that explained, let's see what we do in classification. So okay, in classification, as we have seen that we have our training data looks like this. So you have certain xi and yi. So xi can be a continuous quantity. We don't have any bound on that. It can be anything. So let's say it is 0, and the output label, the class label for this is 0. For 1 the class label is 0. For 2 the class label is 0. For 3 the class label is 0. And let's say past 4, 5, 6 the class label becomes 1. So it's a simple classification problem in 1D. So you have a variable x which increases in this direction, and you have x equal to 3. Here you have a classification label 0, and here you have classification label 1. Very simple, right? Now the issue is that the function that we are trying to learn, it has discrete outputs, right? It is value zeros and ones. And the tools that we have seen so far, let's say regression, the output is a continuous variable. So we have to modify the problem slightly in a way that we get outputs which are a representation of these discrete outputs. One of the things that I would like to highlight again is that if you have discrete outputs, the derivatives are not well defined. Okay? And if derivatives are not well defined, then you cannot use something like steepest descent or gradient descent, right? So let's say you want to write this as a function. So you would have something like that. It would be, how many of you are familiar with Dirac delta function, Dirac delta? Okay. Okay. So you would have a delta for delta y equal to 1 for all the x's which is less than 3, and another delta at y equal to 0 for all the x's greater than 3. But I'm not going to go into this because the derivative of Dirac delta function is of course infinite, because it's just shoots up to 1 at one point, to infinity at one point, and it's 0 everywhere else. So that's an issue. So a way around this is that rather than outputting what the class label is, we output the probability that you observe that class label. Okay? So we would write a function f, our hypothesis function h, which depends on theta and takes in an input x, it would give you a probability that the output label is, let's say, is equal to 1 when you observe the data and your parameters are theta. So it's telling you that for a data point x, what is the probability that the class label of that data point is 1? Does it make sense? Okay. So I'll give you an example. So your y is this, and your hypothesis function would be something like this. So this would be, let's say, 0.1, 0.1, maybe 0.2, 0.01, and then maybe 0.9, 0.99, and 0.8. So what this hypothesis function is telling you is when you observe this x, the probability that the output class of this x is 1 is equal to 0.1, which makes sense. It's a good hypothesis function. Because this is 0, the class label is 0, we want the probability of the label being 1 to be small. Right? So basically, rather than learning the class label, you just learn the probability of that class label. And similarly for these data points, since they belong to a class label 1, the probability of them belonging to class label 1 is high. Okay? Does it make sense? I'm sorry? No, it shouldn't be all equal to 1 because these are different data points. So for one data point, the sum of probability over all classes is equal to 1. So what you're saying is this. If you have two classes, then for a given data point, the probability of yi equal to 1 given xi plus the probability of yi equal to 0 given xi, this should be equal to 1. Okay? So basically, if h of theta for xi is equal to, let's say, 0.1, then this is of course probability of y equal to 1 given xi, right? So the probability of y equal to 0 given xi for this case would be 0.9. Does it make sense to you? It doesn't? Yeah, so this is a different sample. So for each sample, the probability of it belonging to all the classes should be 1. But I'm just showing the probability of it belonging to one class, which is y equal to 1. I haven't shown the probability of it belonging to class 0, which is 1 minus hypothesis of x. So let me just write it here. I'm just going to, so this is hypothesis of x, and this is 1 minus hypothesis of x. So 0, 0, 0.1, 0.9, 1, 0, 0.1, 0.9, and 2, 0, 0.2, and 0.8. Now if you add them, if you add the probabilities along the row, it should be equal to 1. But you shouldn't add the column because these are different data points. Each one has its own probability distribution. If you take 1,000,000 points, there is no guarantee that the sum of these probabilities should be 1. In fact, it would not be 1 in most cases. But does it make sense? So it's the sum of the probabilities for the classes should be 1. But the sum of probabilities for the data points should not be 1. This is different data points. They have no relation with each other and they are independently distributed from each other. Okay? So now we have made our problem slightly easy. Rather than trying to learn a function which gives us some discrete outputs, we say that most likely we would learn a function which gives us something between 0 and 1. Right? Because it's a probability. We are trying to learn a probability which is between 0 and 1. And that's where function comes in. So, well, it's on the slide, but does everybody know what this function is? It's a sigmoid function. Have you guys seen this before? Okay. So a sigmoid function is, the values are between 1 and 0. Okay. It's actually quite easy to see. So exponential, it's bounded from below by 0. You cannot get negative values from exponent. And it's unbounded from above. It can go to infinity, right? So if you, let's say, if z is approaching minus infinity, exponent of negative z would approach positive infinity, and this term would become 0, right? So as you go in this direction, where z is approaching negative infinity, you are approaching 0, right? And as z approaches positive infinity, exponent of negative infinity would approach 0, and then 1 divided by 1 approaches 1. Does it make sense to everyone? Okay, so that's a simple sigmoid function. So that's basically essentially giving us what we want, right? You can interpret it as a probability distribution because you will get a number which is between 0 and 1. So that's something that in our machine learning language we call an activation function, and we obviously saw a reason for an activation function as to why we need it. Okay, let's say that for some process, I'm not going to tell you exactly what the process is, but let's say for some process we want the output of our neural network to be between -1 and 1, and I have been given this function. What should I do in order to make the output, rather than it going from 0 to 1, for it to go between -1 and 1? Can somebody tell me what should I do? So you are given this and you want to get this, where this value is -1 and this value is +1. It's a very simple operation. It doesn't need a lot of work. I'm pretty certain most of you are smart enough to figure it out. Yes, we just multiply it by 2 and subtract 1. So when you multiply it by 2, this would become from 0 to 2, and then you subtract 1 from it, it would become -1 to 1. Okay, it's just a simple scaling and translation of the function. And these are not the only activation functions that we have. We have this activation function as well, which actually has played a very huge role in the success of deep learning algorithms. Okay, it's called ReLU activation function. Think rectified linear unit. But the definition is very simple. Y is equal to x if x is greater than 0, and y is equal to 0 if x is less than 0. Okay, so basically you can write it, it's the maximum of 0 and x. For this function, you can just write it as the maximum of 0 and x. Okay? So if x is greater than 0, you just get x, and if x is less than 0, you get 0. There is a modified version of this function which is called a leaky ReLU. Again, does anybody want to take a shot at it? If this is y is equal to max of 0 and x, does anybody want to write a function for this? What would this be? What would be the, how would we write this function? I'm going to give you a hint. So think of this as a combination of this and this. I'm sorry? Exactly. So this is basically maximum of x and an alpha x, where alpha is something like 0.1, a small number. Okay? So now for a classification problem, we have formulated it as a problem where we need an activation function which gives us a value between 0 and 1, which we interpret as probability of it belonging to a class. Okay. How would we write a loss function for this or a cost function for this? So one thing, the square loss function is actually not a very good loss function if you have very high nonlinearities in your hypothesis function, because if you look at its profile, it looks something like this. So it has lots of local minimas which are too far away from the global minima. So you might get stuck in any one of these, so you cannot use it. So we formulate another loss function or another cost function. We call it binary cross entropy, and I'm going to introduce it here and we are going to see how it looks. Okay. So for a data point, let's say xi and yi, I define my loss function as j, which is function of certain theta, negative of yi log of h theta of xi plus 1 minus yi log of 1 minus h theta of xi. Okay, and this is called binary cross entropy. Okay. So again, you can see that it has some sort of a switch. So what are the possible values of yi? It's a class label and it's a binary class, so it has a label 1 or 0. Yi can be 1 or 0 in this particular case. So if yi is 1, this term is active and this term is inactive, because 1 minus yi would be 0, so you don't need to look at it. Okay? And if yi is 0, then this term is inactive and this term is active. Okay? And again, it depends on the log of h of theta xi, which is probability, so which is between 0 and 1. So if I want to plot the log of a function between 0 and 1, can somebody help me? So let's say I have x here and I want to plot log of x between 1 and 0. So as x approaches 0, what is the value of log of x? Negative infinity, okay? And when x is equal to 1, what is the value of log of x? It would be something like this. Okay? And if I take the if I take the negative of this, that of course would look like this. Okay? That's actually something that we want. So let me just write my loss function here again. So when I say cost function or loss function, I mean the same thing, so don't get confused by that. Okay? So j of theta is equal to negative yi log of h theta of xi minus 1 minus yi log of 1 minus h theta of xi. Okay, so let's say yi is equal to 1. Okay, so if yi is equal to 1, then this term is active, and the loss is just log of h theta xi. Okay, and you can see that the log is very high for h of theta equal to 0. So it means that yi is equal to 1, you want h of xi to be close to 1 as well, right? Because h of xi is telling you the probability that for that x, the output label is 1. Right? Makes sense to everyone? So if yi is equal to 1, then I want h of theta xi to be close to 1 as well. Simple as that. We just want h to be close to y. If y is 1, make h as close to 1. If y is 0, make h as close to 0. And this actually cost function is doing that. Equal to 1, the loss is 0 when h of theta is 1. Right? So because I've written x here, it might be slightly confusing. So let me write this. H theta of x and log of h theta of x. I think now it should be fairly obvious. If yi is equal to 1, it says that h of theta of x should be 1 as well. Because we would try to, in the cost function, we would try to minimize our cost function or loss function. Right? And it would be minimized. That's the minimum possible value. And you will get it for h of theta x equal to 1. Is it clear? Yes, you. Yes. It's not, right? If it's not, ask. I will explain again. So basically, first I would just ask you a question. What does h of theta x represent? Sorry? Probability that for a given x, the label y is equal to 1. Okay? So basically h of theta is, if you forget about probability, just imagine that h of theta is telling you what is the class label. Okay? So if y is 1, you want h of theta to be 1, or as close to 1 as possible. And if y is equal to 0, you want h of theta to be as close to 0 as possible. Okay? Now I have written this cost function. I say that the cost function is minus yi log of h theta xi. For y equal to 1, of course, the loss function is just, the loss function is log of h theta xi, which I have plotted here. Right? And you can see that it has a minima for h of theta x is equal to 1. So if y is equal to 1, it would force h of theta x to be as close to 1 as possible. That's a good loss function. That's what we want in our loss function. Now let's look at the other term. If yi is equal to 0, what would happen? So if yi is equal to 0, this term is active, and I'm going to plot it in maybe blue. So okay, and if h of theta x is equal to 1 or is approaching 1, 1 minus h of theta x would approach 0, right? And it would be very high, like it would approach infinity, and as h of theta x approach 0, log of 1 minus h theta x would approach 0 as well. Does it make sense? So just simply plotted this function, log of 1 minus h theta of x, and you can see that this is h theta of x, right? So at this point h theta of x is 0, right? And if it's 0, 1 minus 0 is 1, and log of 1 is equal to 0. Okay? So basically what this loss function is doing, it's saying that if y is equal to 1, make h of theta x as close to 1 as possible. And if y is equal to 0, make h theta of x as close to 0 as possible. And that's actually a very good quality that we want. That's exactly what we want in our loss function. Again, if something is not clear, just raise your hand. It's fine. We'll just go through it again. It's good to understand it. Because this is like, I think probably without any competition, the most widely used loss function. in machine learning, this or a variant of this, because this is 2 classes, you can have n classes. But if you understand this, generally cross entropy is easy to understand this. But again, very simple, nothing. If it's slightly confusing, just go home and plot it by yourself in your own time and you would see exactly this trend. So it's basically, this loss function is summation of actually 2 loss functions, and one loss function is active for one class label and other loss function is active for another class label, and both loss functions give us what we want for each individual class label. So for class 1, we want the loss to be minimum for h of theta equal to 1, and for class 0 we want the loss to be minimum for h of theta x is equal to 0. Okay, so that's exactly what it's giving you. Okay. Okay. So now that we have defined the cost function, all our work is based on, of course, finding the gradient of that cost function in order to find the minimas or the optimum weights for our system. So now we have introduced 2 new functions today. One is binary cross entropy and one is activation function, which in our case was sigmoid. And we need to actually find the derivatives of both of that in order to implement the gradient descent of classification network, which would have both of these, a loss function and the activation function. Okay, so I'm just going to quickly derive the gradients or the derivatives of both of these, and you guys would help me because I don't want to make a mistake. Okay, so let's look at the sigmoid first. So sigmoid is okay. So I can write it as 1 plus exponent minus z power minus 1. Okay, and I want to find its derivative with respect to z. Okay, how would I do that? Just applying the power rule for derivatives. This would become minus 1 plus exponent minus z minus 2 and d by dz of 1 plus exponent minus z. Okay, this is chain rule, simple application of chain rule, and we can write it as minus 1 plus exponent minus z. The derivative of 1 with respect to dz is 0. The derivative of exponent minus z with respect to z is exponent minus z times minus 1. So I just remove this. Okay, does it make sense to everyone? Just simple derivatives, simple chain rule. Okay, and then I can write it like this. Okay, and this is sigma z time then I can say that I'm adding exponent minus z and subtracting exponent minus z in the numerator, and this becomes 1 minus z divided by 1 plus exponent minus z. Is it correct, or have I made a mistake? Because I was expecting a sigma here. Yes. I just added exponent minus z and subtracted exponent minus z, and then I've collected 1 plus exponent minus z in one term and exponent minus z in another term. Okay, I was expecting something like sigma z 1 minus sigma z or something like that. Okay, that's the problem. Okay. That's the issue. I had exponent minus z here and I just dropped it, right? So it's slightly wrong. So rather than adding exponent minus z and exponent plus z, because I already have it, I don't have the 1, I have to add and subtract 1. So this was like this, plus 1 and minus 1, and then this is just 1, right? Because I've added these two terms in one term and this term in another term, and then these two would cancel, so you get 1, and then it's minus 1 divided by 1 plus exponent minus z, and you can write it as sigma z 1 minus sigma z. So the advantage of writing it in this form is that in order to calculate the gradient of sigmoid, you don't need to calculate anything new. You don't need to calculate any new term. You can just use the value of sigma z to calculate the derivative of sigma z. That's an interesting property. It makes life a little easy. So does everyone follow this? Nothing fancy, very simple gradients. But if you're not careful, you might make a mistake. I just missed this term and there was a mistake because of this. But this is the derivative with respect to the sigmoid function. So again, we didn't lose much. It's a simple derivative. We can actually calculate it. We had a new cost function. Let's see what, again, if I say cost function or loss function, I mean the same thing. Okay. And let's see what's the derivative of the cost function. Okay. So the cost function of h of theta x is equal to minus yi log of h of theta of x plus 1 minus yi log of 1 minus h theta of xi, and I want to calculate its derivative with respect to h theta xi. So as I change this, what happens? So yi remains the same, right? It's a constant, and the derivative of log of x with respect to x is 1 by x. Okay. So this becomes h theta of xi, and of course it's a summation of two terms, so you can take the derivative of first term and then add the derivative of the second term to it. So plus 1 minus yi, and the derivative of log of this term would be 1 divided by 1 minus h theta xi, and then minus 1. Again, it's chain rule. So I take the derivative of log of 1 minus h theta x with respect to 1 minus h theta x, and then I take the derivative of 1 minus h theta x, multiply the two. Okay. So I don't know, we might be able to compress it into something more compact, but I'm fine with it. I don't want to. I'm good with it. yi minus 1. I'm multiplying minus 1 with this, and 1 minus h theta psi. Any questions, any issues? Just you need to know the derivative of log of x, which is 1 by x. Yes, please.
Question about the
Yes.
Why don't we just use them?
Yes. So the reason for that is that with an MSE function, generally, if you look at the energy profile of MSE function, there are a lot of local minimas which are too far away from the global minima. So the loss function with MSE would look something like this. So these local minimas, these are bad. And with gradient descent algorithms, there is a chance that you would get stuck with these. So that's why we don't use them. We don't use the mean square error. But with the cross entropy loss, generally the energy profile is much better. I cannot draw it exactly, but what I would say is that probably you are more likely to be close to the global minima in value. So it's better behaved, and I have some simulation for that. We can actually have a look at it. Like if you minimize the classification error with mean square error, it doesn't behave very well. But if you minimize it with cross entropy loss, it behaves slightly better. Okay. So that's the reason. I do not know the exact motivation for it, but that's the reason that's being that's quoted for it. Okay. So any questions as to how we derive these derivative equations? Because if you know that, now we can actually solve any classification network for its minima. I can give you like a very deep network, and I can tell you, okay, what are the gradient descent equation for this, and you should be able to do it fairly easily, because we basically know the derivative of everything now, and then you just have to apply chain rule to do the backpropagation. Okay. So if everyone is good with it, we're going to take a small break, 5 minutes at this time, and then come back. When we come back, we will look at neural networks. Okay? Okay, guys, we're going to start now. Guys, can I have your attention, please? Everyone, please. Yes. So let's start by defining what a neural network is. I'm going to put an informal definition here. So neural network is a hypothesis function which is a composition of certain linear functions followed by some nonlinearities. That's it. That's what I'm going to define it here right now. And I'm going to start with an example, and we will see how does it actually help us. So let's say this is an example that I'm looking at. I have the size of houses and I have the prices for that. So what are the tools that we have used so far to actually predict something like that? Okay. Linear regression, okay, and it looks like very good candidate for linear regression. So let's do linear regression on it, and maybe the solution that we would get would look something like this. Okay, it's a good fit to data, but I make a claim. I say that if I give this as my estimation function to, let's say, a real estate company, they will probably fire me. Okay, any guesses as to why they would fire me? Yes. So basically, if someone buys a house from me which is quite small, I'm actually giving them money, and that would probably bankrupt my company quite quickly. Okay. So any ideas as to how we can actually fix it? So well, multiple ways, but the simplest one is probably not have the negative values. Maybe have something like this. So below a certain point, you just have zero. You don't sell those things. You don't do the business in that quantity. Okay, something like this. So that's now, it requires, you can see the non-linearity right away. So there is a non-linearity in your function. So there is a linear relation in the data, but beyond a certain point, you don't want the linear relationship. It's not good for you. Okay, and that's where neural networks come in. So they have some linear relation, followed by the composition of some nonlinear function with that nonlinear relation, and followed by higher level nonlinearities, the composition of linear function and nonlinearities. Now what it does is that it actually allows you to learn very complex relations in the data. So neural networks are actually like, in some sense you can approximate any function with this, with neural networks. They're called like universal function approximators. So let's look at an example. Let's say I'm in the housing business and I'm trying to sell houses, and I want to come up with a model. I have training data. I have sold houses. Let's say I'm good at my business and I've sold, let's say, 10,000 houses. I have data for them, and I want to come up with a model where I tell the model the features of the houses, and it tells me how much money should I sell it on. So all of you guys are smart. Let's just try to find out some features which determine the cost of a house. So the first one is size. We saw it in the previous figure. So let's say there is size. What else matters when you're trying to put a price on a house? Okay, location. Location is I've been told that location is the most important thing in real estate. Yes. Yes, I'm trying to define the input for the hypothesis function, the thing which would affect my hypothesis function. So right now I'm trying to define this x. Okay. What else apart from location? When you guys are, let's say, how many floors? Okay, so I'll call it, let's say, capacity. Anything else? I'm sorry? Condition of the house. Okay. Anything else? Okay. Architecture, I'll call it. I'll combine it. And I use another one, let's say, which is facilities. What are the facilities or amenities available around? Facilities. Okay. So now you have 1, 2, 3, 4, 5, 6 variables, and the function that we are trying to learn is probably some complex function of these 6 variables. Okay. What I say is, this again, these are now, I'm going to make some choices, and these are design choices. You would make these choices depending on what kind of data you have, what kind of problems that you're trying to learn. So I say that probably what would be sufficient for me is something like this. So I take all 6 of these, okay, I multiply them with some weights, I add them up, and then I pass them through some nonlinearity. Okay, I repeat the same process here. I'm not drawing the lines, but it's taking input from these 6 variables, adding them up, passing them through some nonlinearity. Let me just draw it so that there is no confusion. And similarly for the third point as well. Followed by some nonlinearity. Okay. And then I say that all of these combine with some weights, and it tells me the price. Okay. Now if you look at it, between the input and output, I have one layer, right? This is my input, this is my output, so I have one layer here. This in neural network language is called a hidden layer. Okay. So this is the simplest, not the simplest, but the second simplest neural network. So you have one hidden layer. You can have 0 hidden layers as well. And as you increase the number of hidden layers, your network becomes deeper and deeper and deeper and deeper. Okay. So as you are trying to get a deeper network, you just increase the number of layers and continue the process, depending on how complex, how much complexity do you want to learn for your hypothesis function. So again, you cannot arbitrarily make it very deep, because then you will learn then you would go into a region of overfitting. You might overfit to a training set. And you don't want to make it very small as well, because then you would be in the region of underfit. So for your data, for your relation, you have to find the right mix. Okay. There is one other thing, another design choice that I have made here, and that's the number of units in the hidden layer. So I have taken 3 units in the hidden layer. You can change these units. You can have 3, 4, 5, 10, 100. It's your choice. Okay. No, hidden units is not a direct function of the data that you have. But if you have small data and let's say you have too many hidden units, then as a result your network would have too many weights. And if the network has too many weights, then you can run into the problem of overfitting. You understand what I'm saying? So basically, you see I have 3 hidden units and I have 6 input parameters. So the weights that I have in this layer, I have 16 weights, right? For each of these I have 6 weights. So W11, W12 and so on. For this I would have W21, W2 and so on and so on. Okay. Now an interesting thing is that each of these hidden units would learn some property of the input data, some combination, some nonlinear combination of the input data, which would probably tell us, which would probably be something on which the decision of the price of the house is made, right? So for example, it can be something like maybe the combination of size, location, capacity, condition, architecture and facility define the satisfaction of the user. So maybe this would learn something like satisfaction. Okay? Maybe. Okay? And maybe this unit would learn something like, let's say, family comfort. Okay? And maybe this one learns something like community life. Okay? We don't specify these things which are learned. It's something that the network, by looking at the data, learns itself. Okay? These might be something very abstract, something that we don't understand, something which make no sense to us. For example, in the last lecture I gave an example that maybe this satisfaction, it might not be customer satisfaction that the network learns, it might be the satisfaction of a building, which to me, if I tell you that this building is very satisfied, you would be like, oh, come on, what does this mean? But the things that the neural network is learning, it might not be directly interpretable to us. It's some abstract concept on that data. But the advantage of that abstract concept on the data is that it helps the neural network to make the right decision. Okay? There is actually a very interesting discussion in machine learning community that we should not put the prior condition on machine learning algorithm that it should learn something like we do. For example, we look at if you give me this data, I would probably try to find something like customer satisfaction, family comfort, and community life. These kind of variables which I understand from a combination of these. But the computer is not restricted by these concepts that we understand. It can learn something very abstract, something which might even be funny for us, but might give good results. Okay? But the point that I'm trying to convey is that the combination of low-level features, the neural network is learning some high-level feature, abstract high-level feature. And then by composition of these high-level features, it's giving you a result, a value for the for the price of the house. Okay. Yes. Yes.
So like, if you have many layers, one of them will like, this is an eye.
Yes.
Like this is an ear.
Yes.
And like the combination would be like the whole.
Yes.
Okay.
Yes. So if using this example, I think I have it somewhere in my slides as well. I think it might be helpful at this point. We have jumped slightly, but maybe the figure would clear some points if I have it here somewhere. So yeah, so this is what what we are trying to say is that at the input, you have just some pixel values, okay? So these are RGB pixel values, which if you give to a person these RGB values in a vector, it means nothing to us, right? Somehow our brain does this magic that if you, rather than giving the RGB values, like 250, 256, if you showed them as intensity, our brain actually interprets all of this. And what our eyes are actually doing is something similar to this as well. It's not a very good claim, but I just want to show that there is a hierarchy in our visual tract as well. So when you look at an image, the first layers of our visual system are something like oriented gradients. They respond to edges and things like that. So something like that. So those who are in electrical engineering would probably realize right away that these are filters. These are probably, most of them are like Gabor filters. So they would respond to edges. Okay, so here, this part you would find something like edges. The output here would be edges. Then you combine these edges and maybe learn something more complex, some high-level feature, like maybe a feature for an eye, nose, ears, hair, things like that. So at the beginning you learned edges. At slightly deeper layer you learned eyes, ear, noses, teeth, these kind of thing. And at a further deeper layer you would probably learn something like faces, and then you can make a decision about whether who this person is. Like if it's a facial recognition system, then it can make a judgment about, okay, this is this person or this is that person. Can we see that different layers have this? Yes, you can. So it's very simple. You give it an input and then you look at the output here at this layer and see what it is. Probably you cannot do it with this. So you can. You want to see if it underfits to one image or something like that. Is this your question? Like, okay. So again, when you're training deep networks, what you do is you are looking at the validation error as you're training, and you just want to see that. Yeah, you have to. You don't have to, but then you wouldn't get very good results. But if you look at it, then you can decide that, okay, at this level, my network is sufficiently trained. Beyond this, it would be an overfit. But still, this is one of the things that we see in a lot of our data sets in computer vision particularly, that you have dataset biases. So what I mean by dataset biases, so datasets are generally collected by users, and we cannot actually sample all the subspace of faces. Like you would sample it, but it would probably in one region, and then when you train on it, since everything is from one region, so your training set, validation set, testing set, everything is from one region. So then the network you train works very well in this region, but it doesn't work everywhere else. Okay, so that's one of the issue. But yes, a good question. Okay, so everybody understands what we are doing in neural networks. Okay, basically we just have some inputs. We want to learn some complex non-linear combination of these inputs as our hypothesis function. Now a question: when I train this neural network, what are the things that I would be learning? What are the variables that would change? What are the variables that I want to adjust to minimize my error or my loss function? I'm sorry? Yes, so these W1s and W2s. So the superscript 1 represent all the weights in the first layer, superset 2 represent all the weight in the second layer, and that's it. Okay, we would just update some weights and everything would be good. Okay.
You can just yourself, you can just the first layer, right? That's W1 value. After that, it's like.
Yes.
You can only adjust the first one. After that, it will have to go back. Oh, right.
No, you have to update the weights of all the layers.
How it would learn something.
No, you are not adjusting. You are adjusting them with respect to gradients of your loss function.
Yeah, I have to give it sit point at the beginning, at a certain
Yes, yes,
for the first layer.
yes.
And then it will continue its own.
No. So basically, let me just explain. I think there is an interesting confusion, but I understand what you are confused about. So I would initialize W1s and W2s for my neural network. Then I calculate the gradient with respect to both W1 and W2. And I update both of them. Okay? Okay? And then I go to a next point and I will calculate the gradient with respect to both W1 and W2 and update it. So when you are thinking of gradient, don't think of W1 and W2 as separate. Just think of a big vector W, which has W1s and W2s, and you're finding the gradient with respect to those. Okay, that's a good question. By the way, these slides are from Deep Learning AI, Andrew NG, if I'm producing his name right. So you can see his lectures, and these are a very good source as well. So again, the same housing price prediction example. So now that we have introduced neural networks, by the way, neural networks are very widely used, but they're used primarily in supervised learning. Okay, so when you have data. So these are some of the examples where neural networks actually work and work quite well. Okay, so we saw this example of house features and house price thing. Okay, this is the simple example, like just for explanation. This is where neural networks are actually making the money for people. Okay, the annoying ads that you get, like every time you open a website, you get these ads. This comes from here, from this application of that's how IMDb gives you suggestion of which movies you're going to watch. That's how Netflix tells you, like, you have to watch this next. What else? That's how probably Facebook gives you suggestion of your friends. I'm sorry? Amazon, exactly. That's what Amazon is using. These like annoying ads all the time, like, okay, now you have bought this, buy this as well, and just keep on spending money. So we have annoyed you with this. Sorry about that. By the way, the buzz, like the things which get very popular about machine learning are applications of convolutional neural networks, which are neural networks on images. Things like these, like image classification, photo tagging. I'm not sure exactly. I think Google probably uses it now. So for example, if you're doing, I don't know if you did it like 2-3 years ago, the search for image, like you go to Google image and let's say search for, let's say, cat on a chair. So some of the images would be cat on chair, and then some of them would be like totally stupid, like maybe a house or something like that. Because I think previously they were using the tag of the image. For example, if I have an image somewhere in text, and in text there is cat on a chair, they would look at the text and then say the cat is in the, they were not looking at the image itself.
So now they're analyzing everything.
Not necessarily. I'm not saying that they do, but we can do some of it. We can do some of it. We can, for example, if you want to see if there's a cat in an image or not, you can do it quite well. Okay, but pretty soon it's going to happen. It's at least better than looking at the text of the caption of the image. Again, the speech recognition, it's already happening. The suggestion that Siri, when it talks to you, it's using some machine learning. If you have used Google Translate now, it asks you that you can actually write, and it would tell you that you wrote probably this. Have you guys used it? So in Google Translate, sometime, for example, I want to translate Arabic into English, so you just write it, and it would tell you, like, did you write this? So that's also something like machine learning. Machine translation is actually a good application, and autonomous driving is actually a very good application of this. But again, the money actually comes from here, which is because it comes from you guys. You are paying for it when you buy the thing. And of course, for each of these applications, there is some variation in network that you use. So for simple examples, let's say the one that we were doing, like house prices, maybe ads, you would have something like this. So for an ad, for example, if you have to develop a machine learning algorithm which would suggest ads, now the unfortunate or fortunate thing is that the data for this we have generated. You guys have generated the data. So you have your account on Amazon. Let's say you're 35-year-old, you are living in Jeddah, and you are buying, let's say, I don't know, some Arabic movie. So Amazon sees that, okay, a lot of people are buying this movie. Maybe to another 35-year-old, even if they are, let's say, from Europe and they don't speak Arabic, but they are here, they might get suggestion for that Arabic movie. So if you have data like, for example, data for this is like age, okay, location, and things like that, you can use standard neural networks, okay? But then you might have applications like this. Where are these used? For example, when your input is an image, okay? Image, you cannot do something like this. You can, but it would be really, really annoying. So I'll give you an example. Let's say you have a image which is 1,000 pixel by 1,000 pixel. So what is the total number of pixel in the image? 1,000,000, right? So you would have a vector which is size 1,000,000, okay? And let's say the number of hidden unit is, let's say, 1,000, right? So now the matrix, just the weights of the first layers would be 1 billion. 1,000,000 times 1,000. And that's just one layer. And then if you make it deep, it's not going to work. So this is very inefficient, let's say, for images. We do something like this. We do something like this. I don't know what to do with it, but I'm doing my machine learning, trying to find the optimum point in the room where it would not. Anyway, so then we use convolutional neural network. So convolutional neural network, basically, if you can actually, does it work? Can you guys, okay. So we can actually think of the input data that we have for our machine learning algorithm in terms of structured data and unstructured data. So structured data is data in which each data point of the input represents something which we understand. For example, in the housing example, if you have size of the house, it means something. We know what size of the house is, okay? And what, okay, let's not say that. But we understand what each data point is. Again, for ads, we understand what user age is, what user ID is, and these kind of thing. But in unstructured data, we probably do not understand each component of the data very well. So for example, if I give you a pixel in this image, there isn't a lot of structure to it, probably doesn't mean a lot. And because of that, if you change a few pixels here, nothing much would change in terms of our interpretation of that data. Again, in audio signals, if you remove a few peaks, I think nothing much would change, you would still hear it. And a good example for that is the telephones that we use. So it doesn't give you the complete audio spectrum. It gives you, I think, like 4K of the spectrum, which is like, I think, a total of 20K. I don't know, some communication guys probably would know it better, but it gives you like a fraction of the audio spectrum, and it works reasonably well, so you can understand what the other guy is saying. There aren't a lot of confusions. So that's the difference between structured and unstructured data. Interesting thing that we have seen over the past 2 days. The reason for success of deep learning is because we have more data, we have more computational power, and we have better algorithms, okay? And this is basically what you guys would be doing if somebody of you is working in machine learning. You would come up with an idea, you would code it, you would do some experiment, and then you would see, oh, it doesn't work, okay? Then you would change your idea slightly, you would code it again, and you would actually go through this maybe, I don't know, for a reasonable size problem for a few months before you find something nice. And the whole reason for understanding the science of what goes behind the neural network is so that you're not completely lost when you're doing it and you're not doing random things. So if you understand what are the equations which govern this learning, you might be able to come up with smart ideas and increase the speed of this process by some margin. informally, we did it yesterday. We went through it informally, like we wrote some general function, but today we write it formally and we try to write all the equations and then try to find the gradients of it and try to see if we can do the back propagation through them or not. Okay? Probably one of the simplest neural network possible because you don't have a hidden layer. It takes in 3 inputs, add them up, pass them to some nonlinearity and give you an answer. Okay, so I'm going to just write some equations and try to label it. So and it has one hidden layer, and that layer has just 1 unit. So the output layer has 1 unit. So you have a weight W11, W12, W13. Okay, you add them up and you pass them to some nonlinearity. So the output here, let's say I call it Z and this A. So what is Z? Z is W11 times X1 plus W12 times X2 plus W13 times X3. Okay, and of course you can write it as W transpose X, where W is W11, W12, W13, and X is X1, X2, and X3. Is it clear? It's basically a dot product between 2 vectors. Okay. We can add a bias term to it as well. Generally, it's always feasible to add a bias term because the inputs would never be able to model the bias. You have to have a separate bias term. An easier approach, I think, at least for calculation, is just add an x4 and make its value always equal to 1. So that would act as a bias. Okay. And then the activation function, so Z is this. And the activation function is just a sigmoid of Z. Okay, and this gives you y hat. Y hat is your hypothesis function. So this is what a neural network does. Then you put this hypothesis function in a KAUST function and try to find the right values of W1, W2, W3. That's done. You are experts in machine learning. You can train neural networks. Any questions there? Any confusions? There must be some, right? Okay, so let's look at slightly more complex neural networks. So we looked at a very easy one and wrote the equations for it. Let's do the same thing here. So for the time being, I'm just going to ignore the bias. Let's assume that x3 is equal to 1 and that's the bias in the network. So all the weights of the first layer are going to have a superscript 1. Okay. The first argument of the weight subscript tells you the unit and the second tells you the input. Okay. Sorry, this is 1, 1. Okay. This is W1, 1, 2, W1, 1, 3. Okay. So I'm going to call this Z1. So the first element of Z1 is equal to W1, 1, 1 times X1 plus W1, 1, 2 times X2 plus W1, 1, 3 times X3. Okay, everyone agrees with this? Okay. Similarly, we can do it for the second element of Z. That would be W21 X1 plus W22 X2 plus W23 2, 3, x3. Okay, and similarly for the third element of Z1, W31 x1 plus W32 x2 plus W33 x3. Everyone agrees with it? So it's just putting some weights on these. So basically, let me just write this for this. So this is W31, W32 and W33. Okay? Yeah. So would everyone be okay if I write these equations like this? Z11, Z12, Z13 is equal to W111, W112, W113, W121, W122, W123, and W131, W132, and W133, X1, X2, and X3. Okay. I just collected all the equations together and I wrote them in a matrix form. Superscript is for one layer because I'm looking at the first layer. Okay, any confusion here? There are questions, ask them. Cannot be any bad questions. If there is any confusion, ask them. Okay, so I'll assume that everything is good. Past that I have to pass them through some activation function. Oh, I have Z4 as well because I have 4 hidden units. So Z14, I can write 4.1, 4.2 and 4.3. Okay, and then if I have to find A1 is the output of the network after the activation function. So you can say that A is just the activation function of the vector. So it's an element-wise operation. You do it on each element and you're done. If it's sigmoid, you just take the sigmoid of each individual element and you're done. Now let's look at the second layer. So you have W2, 1.1, W2, 1.2, W2, 1.3, and W2, 1.4. Okay. Again, you can write it in matrix form. So that would be A1 times W2 transpose, where W2 is Does it make sense? And you can call it Z2 because it's the Z of second layer. Okay. The output of each linear transform, let's call it not a linear transform, of matrix multiplication, I call it Z, subscript the number of layer, and the output of each activation I call it A, superscript the number of layer. Okay. So basically now you have found Z2, and in order to find A2 you just do the activation function on that. Pass it through the activation function. Any questions there? Any confusions? Just a simple vectorization of the process. Okay? Vectorization is important because otherwise you cannot keep track of each individual weight. It's good to do it in matrix form. It's very compact and it's easy to keep track of things in forward pass and backward pass. So again, just to explain that we are doing this step. We're just calculating Z's, which is the output following the matrix operation, the matrix multiplication, and then an A, which is the output following the activation function. And here I am just slightly neatly written, but this is what we are doing. For Z1, we have W1 transpose times X plus B1, and then for A1 you just take the activation function of that Z1. For Z2 you have W2 X transpose X plus B2, and then you take the activation of that and so on. Okay, and then you just collect them, and that's it. So if you have a multiple layer deep neural network and you have to find the output, this is what you do. You start with X, you find Z1, the output of the first layer, you pass it through the activation function, you find A1, you take A1, you find Z of the second layer, Z output of the second layer following the matrix multiplication, and then you pass it through an activation function, and you repeat this process. If you have n layers, you do it n times, but nothing complex. Basically, every time you're taking a vector, you're multiplying it with the matrix, and you're doing some element-wise operation on that. Activation function are sigmoid, it's non-linearity, so forget about activation function, let's call it non-linearity. So you take your the output of your matrix multiplication and pass it through some non-linearity. We do non-linearity, so I'll just give you one example. I think that's a good question. We did it yesterday, but let's do it again today. So the activation functions are basically non-linearities in the network. So why do we need these non-linearities? Okay. The reason for using these non-linearities is that these non-linearities actually build the capacity of your network as you compose multiple layers. Okay. So we saw sigmoids and we saw ReLU. These are actually the activation functions, and both of them are non-linear. So sigmoid is also a non-linear function, ReLU is also a non-linear function. But if we don't have these non-linear functions, how would our neural network look? The wrong neural network would look like this. It would have an input X, you would take its matrix product with W1, let's say, you would have some weights in the second layer, you would take its matrix product with W2, let's say you have 3 layers, and you would take its matrix product with W3. And for the time being, let's assume that n was of size 10 by 1. Okay, give me any number, any like large number for the size of W. Of course, the columns of W1, the column of W1 have to be 10. How many rows do you want in W1? Any number. Say any number. 1000, okay. So W1 is 1000 by 10. How many rows for W2? Okay, 1000. I will change it, I'll make it 999 so that we can see the difference. So 999 multiplied by 1000. And for W3, let's say 1, output layer is 1, because let's say it's a binary classification problem. Okay, so 1 multiplied by 999. So your network without non-linearity is just composition of linear operations. So you take a matrix, you multiply it with an input, you multiply it with another matrix, multiply it with another matrix, and multiply with another matrix. Now let's say I just take this part of the network and see what this is doing. W1 composed with W2 composed with W3. So my claim is that if you multiply W2 with W1 and W3 with the answer of these two, you would just get a vector of 1 by 10. And you can see that. So it's a matrix multiplication. When you multiply W1 by W2, you would get an output which would be 999 by 10. and then when you multiply that output with W3, you would get an output which is 1 by 10. So basically, whatever you learn with this network without nonlinearities is equivalent to what you can learn with just 10 weights. So a lot of weights are just not used, like they're useless. You can train with respect to them, but you wouldn't learn anything new. You can just learn everything with a vector of size 10. And our network had, let's say, 10,000 and then a million, and so you had a million and 10,000 plus weights, but what you learned was just you could learn it with 10 parameters. That's why we need activation function. That's why we need nonlinearities. Okay? Because if you have a nonlinearity here, then things change, right? You cannot decompose them as just two linear operations because you have nonlinearity in between them. Does it answer your question? Okay. Okay, so we actually have done this. We have done vectorization for a single sample, right? So basically now if you have an input sample X, you want to find the output of the neural network, this neural network, so you can multiply it with the weight of first layer. Okay, I'm going to drop the bias. Okay, for me bias is inside X. Okay, I pass it through some activation function, I multiply it with a second layer, I pass it through some activation function, and that's it. That's my output. Pretty convenient notation. But if I have, let's say, data points xi's and yi's, which I is, let's say, from 1 to, let's say I have 1 million data points. I don't want to do it for each individual one of them in a for loop, right? If I want to do this operation, I can write a for loop. I can say that for I equal to 1 to 10 power 6, do this operation. Let's call that this f. So just calculate f of xi. Okay? That's, I think, a big waste of resources if we try to do it like this. Is there a way we can do it in a slightly more efficient way? Anybody wants to take a guess? Yep. I'm sorry? Recursion, okay, that's one thing, but you would still have to go to each element, right? Anything else? So I'll give you a hint. So the hint is that X is a column vector. So this is an Xi that you put here. Now, can you give me what to do? Can you guess? Just stack the inputs, okay? Rather than having an Xi as one input, just stack X1, X2, X3 and up till X10 to power 6 in a matrix. And if you do it, then I can say that F for all the data is just sigma W2 times sigma W1 times a big matrix X. Okay, so it's a matrix operation. It would do the operation for each column, and it would give you an output in each row, in each column of F. So rather than doing it with a for loop, you would do it with a vector. And the reason is that vectorization almost always increases your speed rather than using a for loop. If you use a for loop, you would have to do each operation. So let's say your CPU is capable of performing 100 operations at a time, but your for loop is asking it to go take one pair and do an operation, take another pair and do an operation, take another pair and do. You don't need it. You can make it a vector, and your CPU would automatically do all these 1,000 operations in a single step. So that's why we do vectorization. That's why we want to write it in compact representation. But just for your data, just stack all the input data in a matrix. Call this matrix X and use that in your notation, and you would be good. Okay. So this is what we do without vectorization. Okay, you just have a for loop, and we say rather than having a for loop, do this. Take a big matrix X, where you have X1, X2, X3 up till Xm, and then you, in order to find Z1, you can just do this W times X plus B, right? So now Z is not one vector, it's a matrix. Each column has Z for one element of your data, one column of your data. And if you want to find A, that would be just an activation of C. Previously you were applying it element wise to a vector, to a column vector. Now you would apply it element wise to a matrix. Okay? Each column of that matrix, each element of each column of that matrix. And similarly Z2 would become W2 times A1, and A2 would become sigma Z2. Okay. Should be fairly clear what we are doing in vectorization. Okay. And now you can see that this is what would happen. So you just stack your data in columns, and then the output Z that you get would be stacked in columns. The output A that you get would be stacked in columns. The output Z2 that you would get would be stacked in columns. The output A2 you would get would be stacked in columns. By the way, what would be the size of this Y hat? Let's assume that I have 1000 data points. My input data is of size 1000. What would be the size of this Y hat? Somebody should answer. It's not that complex. Just raise your hand and answer it. Do you want to guess? Sorry, it depends on what? You have just 1000 data points, right? So what would be the size of Y hat? Let's say you give it one input. You just have one input. What is the size of Y hat? 1, right? If you give it 1000 data points in this form, in this matrix, what would be the size of Y hat? 1 multiplied by 1000, right? You would have a row vector where each column would be the output for each data point. So if you stack your input data like this, your output data would also come like this. So basically Y hat would be like this. Y1. Okay? Nothing complex. Everybody agrees with this? Any questions? You don't look very happy. You don't seem convinced. Yes? You're convinced, huh? Okay. Okay. So we're just going to do a short discussion of activation functions. So, and after that we would end, and the rest we would continue tomorrow. So we basically looked at two activation functions, sigmoids and ReLUs. The sigmoids and some other activation functions, tan hyperbolic, etc., which are similar to sigmoids, were actually popular or were used quite a lot, and ReLUs are relatively newer. But when we had sigmoids and tan hyperbolic, we couldn't train very well. Our neural networks were not trainable with a lot of success. Anybody wants to guess as to why this was the case? So I'm making a claim that if you have a deep network and you are using sigmoid activation functions, you would not be able to train it very well. Okay? So for our training, what are we using? What are the algorithms that we use to minimize our loss function that we studied up till now? Gradient descent and stochastic gradient descent, right? And what do these algorithms use? What does gradient descent depends on? The gradient, right? The derivative. And what is wrong with sigmoid in terms of derivative? If you look at the derivative of sigmoid, how does it look? So what is the derivative of sigmoid in this region? What is the derivative of sigmoid in this region? That's not a very good property, right? So the derivative of sigmoid is 0 for a lot of the range of the input. And then you have composition of sigmoids. You can expect that it would be 0 for quite a lot of the region. And if it's 0, then the gradient is 0. And if the gradient is 0, then you're not going anywhere. If you're doing gradient descent, you're just standing there. So this is called the problem of vanishing gradients. Okay? So your gradients just vanish and they become very small. Let me just draw the gradient of sigmoid here for those who don't understand it very well. So the gradient of sigmoid would look something like this. So it's not to scale. So this might be up and down. I haven't drawn it to scale, but this is how it looks. It's non-zero in certain area, and then after that it's just 0. And that actually created some problem. Like, we weren't able to train networks of sufficient depth, because if the gradients are 0, well, you cannot go anywhere. So you wouldn't be able to find something nice. And this problem was solved to a good extent by using something like this, ReLUs. So that's the advantage of using ReLUs. So what are the gradients of ReLUs? How many possible values of ReLUs gradient can you find? Ignore the point at 0. 2 values, right? 1 and 0. So for most of the range it's 1, which is very good. Again, you can have this region less likely than in this case. So in this case, the entire domain was almost 0. There you had a very small region where you were good. In this, at least half the domain is good. But even if you want to fix this, you can use something like this. And then you are good. You have a gradient defined everywhere except at point 0. Okay? And of course, gradient is defined here for these as well. You have a non-zero gradient, a defined non-zero gradient everywhere except for point 0. And that's actually one of the reason for that we are able to train deep networks. We can use this activation function. So this activation function is like very popular, unless there is some very special case. You would generally use these activation functions. So this is quite commonly used for deep networks. You have sigmoids and things like that, and softmax in the output layers, and generally all the other layers are ReLUs. Mostly. Of course, you can have special cases. Okay, any questions? Any suggestions? Yes? Yes?
We try to update the
No. You have to do so. We will have a look at it, but so let's see if I can find a clear page. Yes. So when you're trying to update the weights of the network, like I said, imagine that all the layers are stacked in a big vector. You find, so basically, let's say I have a layer for I equal to 1 to number of layers, right? And I'm finding gradient I, where gradient I is the gradient of the loss function with respect to the weights of that layer. Okay, so I have to do this first. When this loop finishes, I would write an update loop. So I would say for I equal to 1 to number of layers, do this update weight. So weight I, weight t plus 1 is equal to weight t plus minus gradient I times some factor alpha. Okay? You don't do it sequentially, because if you do it sequentially, it's not exactly gradient descent. Okay, because you're not calculating gradient. You calculate part of a gradient, you took a step there, then you calculate another part of the gradient and you took the step there. Because essentially the definition of gradient is that you stand at a point, you find the derivative in each direction, and then take a step in the direction in which it changes most. But let's say if you're standing at a point, let's assume that direction is not just a direction, it represents a vector W in my complex space. And you find the gradient with respect to W and you took the step, then this was not the gradient direction, because the gradient direction you have to find the gradient with respect to W1 and W2 and W3 and all the W's, and then take the step in that direction. It might still work, but it's not gradient descent. So for gradient descent, you find the gradient with respect to all the weights and then update them together. Then you go to the next point, you update with respect to, you calculate the gradient with respect to all the weights and update in a single step.
Because the way that because we have the weight 1 and then we put into the activation path.
Yes.
After that we have the output and then gain.
Yes.
So that's why
So yeah, I got that. So basically what you're saying is that since our so since our network looks like this, so you have W followed by sigma followed by W2 followed by sigma, X is here, and you have Z1, A1, Z2 and Y hat. So you're saying that you calculate the gradient with respect to the gradient of Y with respect to W2 at this point and update it and so on. Yeah, but you don't need to do it, right? You calculate the gradient with respect to W2 and store it and calculate, like keep going back in this direction and calculate the gradient of Y hat with respect to W1 as well and then update. So just we have 3 minutes. Hopefully I would be able to write the expressions in that time. So let me just write it for you and we can actually see it. So what would be the gradient of Y hat with respect to W2? That would be the gradient of Y hat with respect to Z2 times the gradient of Z2 with respect to W2, right? So that's one, you calculated it. Let's write the other one. You already have the gradient of Y hat with respect to Z2. So I'm going to say the gradient of Y hat with respect to W1. That would be the gradient of Y hat with respect to Z2 times the gradient of Z2 with respect to A1 times the gradient of A1 with respect to Z1 times the gradient of Z1 with respect to W1. So nothing is stopping us from calculating both of them simultaneously. Yes. In which sense? Like a feedback loop, in what sense? Now of course there is a feedback loop in a sense that once you updated your weights, all Z1, Z2, A1, A2, all of them would change. So that's the feedback in some sense. Make sense? So you change something, it's not like you don't change any of the output, all the outputs would change. So if W1 and W2 change, Z1 would change, A1 would change, Z2 would change, and A2 would change. So basically the value of your function would change because you have to find the gradient of the function, so you have to be on the contour of the function. And then of course, so it's not blind, it's not like you're just changing something and nothing is changing. Everything else is changing. So once you update everything, you would do another forward pass, you would calculate all these variables again, then you would do another backward pass, you would find the derivatives of everything again, you would update it, then you would do another forward pass, calculate all the Z1s, Zs and As again, update all the Zs and As, and so on. Yeah. Hopefully it's not. Yeah, it's you can actually write it in an efficient manner so that you don't have to store too many things. Okay, because there is a relation between activation function and z, which you would see. So you can actually, you don't need to store both of them in order to find the derivative. For example, if you're using if you're using ReLose, you don't need to store z. You can just you don't need to store a. You can just store z. Right? Because the derivative of a with respect to z is either 1 or 0. So you can say if z is greater than 0 multiplied by 1, if z is less than 0 multiplied by 0. Okay? And things like that. Again, if it's sigmoid, you also don't, for its derivative, you would just need the value of the sigmoid. So you can do these smart tricks in order to preserve some memory. But yes, overall it would be a memory intensive operation, because if w's are big, then it takes some memory. Okay, any questions? I hope it's not terribly confusing and complex. It's easy. Just like do some of it on, take 10 minutes on a paper and you would learn everything. Just do it by hand. Okay. Thank you very much.